All right, so I did get a few questions by email, so I'll go ahead and answer those first. The first considers drawing was about drawing Fischer projections of cyclic molecules. And there's actually a couple ways you can do this, but let's start with how we translate a Fischer. Well, let's start with a harder example first, which is a Fischer projection of a linear molecule. Now, the challenge with drawing the Fischer projection of a linear molecule is that the Fischer projection is not actually a representation of that stereochemistry we've got drawn per se. The way a Fischer projection actually works is if we were to take this six-membered ring and loop it around. So we'd have to rotate bonds in order to recreate this looped compound. So this is what your Fischer projection really looks like if we were to draw what it's representing. So this is the molecule I've got drawn up on the board. These are my ones that are popping out. In order to draw the Fischer projection, I actually have to rotate it around into this loop structure and then start drawing the Fischer projection as I start looking along the loop. So your Fischer projection looks like this. It doesn't really look like this if we were to draw it out stereoscopically. So how do we do it for a cyclic molecule? Well, for a cyclic molecule, it's actually pretty easy because it's already in a loop. But what can throw people off is how this would actually get translated into a drawing. So with linear, it's really easy. We see the top and bottom terminations because that's in the molecule. So what we're going to do to draw the Fischer projection of, in this case, cis-1,2-dimethyl cyclopentane, is we're going to extend one bond. We're going to make it really, really, really long. And as we grow it out, we're going to end up getting a rectangle. Now, there's a couple ways you can draw the structure. It really doesn't matter which one you do. I have my preference, but honestly, you're right regardless of what you do. First option is I like to take CH2 groups and make them the starting and ending parts of my box and just draw CH2s in the corners. And the reason I do this is your CH2 groups here, they don't have chirality. The whole point of doing a Fischer projection is to accent the chirality. So I just make them the corners. It's easier to draw. Another option is that you can say, we can pick our two carbons and we'll just go ahead and draw them like we would in a normal Fischer projection. This is probably the more correct way to do it, but honestly, it's not going to change your answer. The complication here is that you do need to define your starting and finishing position. So let's say this green carbon here is my starting position. So this is going to be my starting carbon. And then my last carbon is here, my finishing position. The only thing I have to do for this Fischer projection is make sure that I'm consistent with everything else. So I've got 3 carbons between them. 1, 2, 3. And anything that is a wedge is going to go onto the left side. Anything that is a dash is going to go on the right side. So if I've got a wedge, I've got a CH3 here, CH3 here, and H, 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 and H. So in terms of drawing these molecules, it's actually pretty easy. Instead of having these terminal groups in the end, we're just going to create a loop. And we need to pick 2 carbons, doesn't matter which ones we pick, in order to be our top and bottom carbons and make sure we draw everything else along the line. Now, here's the problem with cyclic molecules. Where you start and where you finish is going to really dictate if the Fischer projection is going to make it apparent which are the meso complexes. So meso complexes are ones that contain they have more than one chiral center and there's a mirror plane running through them. So for something like this, it's really easy to see that there's no mirror center because we have the whole molecule. But here, depending on where we start and stop in the Fischer projection, it's not as apparent if there's any mirror planes. So if I have something like, well, this complex, here I don't see a mirror plane on the drawing because I can't draw a line here and say, oh, there's a 1-to-1 correspondence on both sides. But if I look at the line bond drawing, I definitely see that there's a mirror plane, so this is a meso complex. So yeah, that's kind of how you draw a cyclic molecule using using Fischer projection. Now I have one other question to answer before I get to yours, Elijah. It's the carbon-13 NMR spectrum from the Organic 1 discussion board. So you have A carbons, B, C, D, E. And in the discussion board, carbon-13, 1, 2, 3, 4, 5. Chemical shifts, 47.3, 45.7, 30.6, 29.5, 15.1. And we have an integrated area of 11131. So in terms of tweezing out the chemical shifts, integrated area, this problem makes it pretty easy. There's only 3 A carbons, so this obviously has to be the A carbons because there's 3 of them. How do we tweeze out the rest? Well, the more hydrogens we have bonded to our carbon, the more shielded it's going to be, so the lower its chemical shift. So the most shielded here is going to be carbon E, because it's got 3 hydrogens, that puts E here. And our least shielded here is B. So C and D both have 2 hydrogens. How do we tweeze out which one's more shielded, which one's more deshielded? Well, we just look at what's beside them. This has the more shielded carbon, which is going to give some shielding to this D carbon, giving it a slightly lower chemical shift than the C, which is beside the most deshielded carbon. So just go B, C, D after that. And that's how you work out the carbon-13 NMR for the discussion board. When you're ready, you can go to number 3, number 33, number 36 in the homework, and this is for Organic 2. So let me bring up the homework. Question 33. Evaluate the cyclonona tetraene to decide what species is formed, whether species is aromatic form. So loss of hydrogen from the sp3 carbon. Let me draw it first. So we're going to lose a hydrogen from the sp3. This is going to give us an ion. First question, is it cyclic? Yes. Is it conjugated? Yes. We have 1, 2, 3, 4, 5. These are all conjugated. So now the question is whether it's aromatic. So we need to see if this follows the 4n+2 rule. The n here is just a generating function. It's a way of quickly determining if something has the correct number of electrons. So if it contains 2, 6, 10, 14, 18, so forth, it's aromatic. If it doesn't contain that, if it contains 4, 8, 12, 16, it's anti-aromatic. So now we start counting them up. 2, 4, 6, 8, 10. We have 10 electrons in this compound, so this would be considered an aromatic complex. Now, question 37. Or question 36. Hey, you're very welcome. This one. Okay. The one I can't seem to delete because it's actually tied to like 3 other courses right now. So for this question, what's not shown here is that boron actually has a vacant p orbital. This is why boron evades the octet rule. So actually it is cyclic and it is conjugated, but boron here contributes 0 electrons to the ring. Nitrogen is going to get through using its lone pairs. So we're cyclic, we're conjugated, and we've got 6 lone pair electrons. So if we do the 4n plus 2, it's not 2, but it is 6. So this would also be considered aromatic. So it's kind of a weird one. I was trying to delete this problem, but for some odd reason, because it's shared among the courses right now, I'm not allowed to delete this question. But it is kind of a weird question. You just have to know that boron has a vacant p orbital, which I don't really think is quite fair. All right, other questions? Yeah, you just have to recognize boron doesn't have any. It's basically the antithesis to nitrogen. All right, other questions? Did you give another example of finding out chirality with rings with a double bond like benzene? So any carbon that contains less than 4 bonds is inherently not chiral. So let's say we have this molecule here. So first of all, off the bat, having stereochemistry does not imply that the center is chiral. It implies that it has the potential for chirality. So we look at carbons, we only consider those that are considered sp3 hybridized, or more specifically, it's carbon that has 4 bonds. So terminal methyl groups don't count towards chirality because they're CH3s. Now, this can't be chiral because it doesn't have 4 bonds. So we need 4 bonds around the carbon to imply chirality. Now, this does have stereochemistry. So in this case, we would say this is a Z conformation. Now, organic 1, you haven't gotten to this point yet. When we start talking about alkenes, which I think is test 4, that's when we'll start talking about the EZ notation. But the only carbon here that stands the potential of being carbon is chiral is this one here, because this one has 2 methyl groups hanging off it. So in terms of chirality, so I see what you're getting at here. We will write, if we look at this carbon, it's got a hydrogen bound to it, a CH3 group, a carbon bonded to two methyl groups, and a carbon bound to a methyl group and double bonded. So the shorthand we use for this, if we want to figure out the priority, is that we write out the atom that it's bound to, and then we write out what each of the bonds are connected to. So this carbon has 3 hydrogens bound to it. This carbon has 2 carbons and a hydrogen bound to it. So it's got that carbon, and not drawn is the hydrogen behind it. For this carbon, it's bound to a carbon, and it's actually double bound to another carbon. So we're going to write out each bond as a carbon. So that's a C, and that's a C. So in terms of assigning priority roles, hydrogen is going to be the lowest, 4. In terms of what's bound to it, we're going to look for the first difference. So this is carbon, carbon, hydrogen, because this has the lowest atomic number. This will be third priority. Between these, first one's a carbon, second one's a carbon, the third one here is a carbon, this one's a hydrogen, so this makes this the highest priority, and this makes this the second highest priority. So if we have double and triple bonds, basically we just treat each bond as if it was a single bond to the same element. So the example in the molecular modeling lab had you working with an aldehyde. And so this is going to be your chirocarbon because it's the only one that has 4 unique groups bound to it. In terms of what's bound to that carbon, we've got a hydrogen and an oxygen. So the oxygen is a higher atomic weight than both the carbons and the hydrogen, so this ends up being top priority. Hydrogen is the lowest. And if we want to figure out the priority of this one, or this one, we're going to look at what it's bound to. So it's bound to 2 hydrogens and an oxygen. Oxygen is the highest atomic weight, so we'll put oxygen first and our 2 hydrogens. Now this carbon is bound to an oxygen and a hydrogen, but it's double bound to the oxygen. It's double bound to the oxygen. So we're going to put the oxygen twice, 1 for each bond, and then we're going to put the hydrogen in there. Now we look for the first point of difference. So oxygen, this one has oxygen and hydrogen. This makes this one higher priority, and this one lower priority. So in terms of like double, triple bonds, again, we're just going to treat that double bond as if it's 2 bonds to the same element. That triple bond is if it's 3 bonds to the same element. All right. Do you have to for aromaticity, do you have to multiply the number of lone pairs by 2 or just take into account the actual number of lone pairs that are present? So you can, this is where the parlance is really bad. Take the number of lone pairs and multiply by 2 because what you want is the number of lone pair electrons. And for every lone pair, there are 2 lone pair electrons. So yes, if there are 2 lone pairs, that would be 4 electrons, not 2. Because we don't care about the number of lone pairs, we care about the lone pair electrons. That's why we also multiply the number of double bonds by 2, because there are 2 electrons in each of those bonds. Other questions? Yes, because what makes them an anion is that they have a lone pair. And again, we're only going to focus on carbanions and carbocations for the positive negative charges. We're not going to have something like oxygen anions or nitrogen anions, just to keep it simple. But what makes a carbanion versus a carbocation are lone pairs. So your carbanion has that lone pair to give it the negative charge. Your carbocation doesn't have a lone pair. Hey, you're welcome. Could you go over question 58 for homework, for the Organic 1 homework? All right. Almost there. How many rings are present on C11H18 if the compound consumes 3 moles of H2 on catalytic hydrogenation? So, teach this because we have to. So, any linear, so we'll start with C11H18, any linear alkane is going to have the formula CnH2n plus 2. So if we just had a purely linear saturated alkane, we'd have 24 hydrogens, but we're short 6. Now, there are 2 ways we can lose 2 units of hydrogen. One way is through carbon-carbon bonds, which are going to be our rings. The second are through unsaturated bonds. Now for each of these we have 2 hydrogens. So for a carbon-carbon bond, basically we remove the hydrogens, and where the hydrogens were, we connect the carbons. And for unsaturated bonds, this is where you get to your alkenes, alkynes, and so forth. So catalytic hydrogenation can only account for these. So we have a difference of 6. That means we have 3 degrees of unsaturation. Now, if we have, for every double bond, we would eliminate 2 hydrogens. So if we're absorbing 3 moles of H2, that means that we have 3 unsaturated bonds. And that would be 6 hydrogens total. So if we've lost 6 hydrogens, that's all accounted for in unsaturated bonds, so we would say that there's no rings here. Now, if it said you use 2 moles of H2, well, that's 2 unsaturated bonds for a total of 4 hydrogens. So we've only accounted for 4 of these 6 missing hydrogens with double bonds or triple bonds, which leaves us with 2 unaccounted hydrogens, which have to be the rings. And this is going to play more into helping you figure out the number of different isomers. This is kind of a question that I do think shows up on the exam, is that given this formula, how many different isomers can you conceive of? Now, full disclosure, problems like that, so if it gave you the C11H and I said, how many different constitutional isomers are there? You couldn't figure it out. There's just way too many possibilities. So particularly for the exam, we stick to simple things like C2, C3, and C4. These can get super, super complicated in terms of figuring out all the different possibilities, so we'd like to keep the numbers short. But just in terms of guessing how many rings there are, take the number of moles of H2, multiplied by 2. That'll tell me how much hydrogen deficiency can come from those double bonds or triple bonds. And use this 2n plus 2 rule to figure out how many hydrogens you're deficient. For every 2 beyond the hydrogen uptake, that's a ring. I know I didn't say that very eloquently. Yeah, and for this problem, it's 0. For the logic for predicting isomers, there isn't one. It's all guess and test. And this really shows up if you go to the practice packets that are on the course website. So let's say I give you C3H4, 6, 8, C3H4. Ooh, that's a tight little molecule. C3H6. This seems really simple, but we have that 2n plus 2 rule. So we have Cn, H2n plus 2, and really if we had 3, we expect 8. So we have 1 hydrogen missing. So this can either be a double bond or a ring. So if we do the ring, we can get this. If we get a double bond, we get this. So for C3H6, this looks pretty straightforward. Now let's say we go to C3H4. Well, in terms of unsaturation, we've got 2 degrees. So we could have 2 double bonds. We can have a triple bond. Or we can have a ring plus a double bond. So by getting rid of those 2 hydrogens, we introduce 3 molecules. So by getting rid of hydrogens, we actually start creating more and more possibilities, which you would probably think would be the opposite. The more hydrogens we get rid of, the more options we limit. Now when we go to something like C4, so something like C4H8, we have 1 degree of unsaturation, which can give us 1 ring or 1 double bond. Well, we can have a ring like that. We can have a ring like that. For a double bond, we can have a terminal double bond We can have a central double bond, but for the central double bond, we've got two stereoisomers. We got the cis and the trans. So just by eliminating two hydrogens, now I've got 5 possibilities. Now if I eliminate 2, I can have 2 rings, or I can have 2 double bonds. I could have a double bond with a ring. Basically, this all quickly begins to escalate into a lot of guessing and testing. And when I first started making the keys for those packets online, in class examples, we would come up with more solutions to it. So predicting isomers, even your book concedes that there is no approach. There's no algorithm you can use. It's basically how clever you are, how many different possibilities you can come up with. And if you do something like C5, this gets more and more complicated. So something like C5H8, we can have 2 rings. 1, 2, 3, 4, 5. And still get this C5H8 possibility. Like, or we can do something like that, or something like that. That will still get us everything we would expect for C5H8. So for test questions, we typically keep it very simple, but because we can start wandering off into these really complex structures, we're limited in terms of the number of practice problems we can actually do. So predicting isomers, again, we always have to stick to simple examples because there is no algorithmic way to predict all the different types of isomers. It's mostly lots of people coming together, coming up with lots of different possibilities and seeing when we run out of ideas. So it's a hard concept. Unfortunately, we don't have a lot of examples because there aren't that many doable examples. Yeah, you're welcome. Yeah, I'm sorry. I really wish I could give you like a good algorithmic way to go through and predict the isomers, and I've tried to come up with ways of doing it by myself, but every time I do it, I pick something like C5 or something bigger that I don't know the answer to. I come back the next day and I think of more possibilities. So there really is no algorithmic way to do it. Other questions? Ah, of course. An example of Friedel crafts. So Friedel crafts, there's the alkylation and isolation. Now both are going to utilize FeCl3 as a catalyst, and what they're going to end up doing is attaching our R group to a benzene ring. So for now we're just going to ignore the directing groups. Now with the alkylation, this has to be a secondary or tertiary alkyl chloride. So we can do something like 2-chloropropane, or we can do, I don't know, something like that. But the reason why we can't do a primary is that this is going to go through a carbocation intermediate. So if we try to put the chlorine here, when we generate our carbocation, we're going to get a hydride shift that'll put it here, and we'll be back to secondary attachment. So your alkylation here is going to do second and third alkyl chlorides. Your acylation is meant to get around this problem. So your acylation, an acyl chloride, is basically, it looks like an aldehyde, but in place of the hydrogen, you've got a chlorine. So when we generate the carbocation here, it doesn't move from the carbonyl carbon. The drawback is that if we want to go from an acylation to a alkyl benzene, so something without a, move your camera. There you go. So if we don't want to finish with this carbonyl here, we're going to have to do subsequent reductions. So this is where your Wolff-Kishner, your Clemenson, and your Bozingo reductions will come from. So if we want to go from this to this, you're going to have an additional step. But the advantage here is that we can do we can make it look like we're attaching a primary alkane to the benzene ring. So if we want to attach something like propane, we would do this propyl acyl chloride, attach it, and then reduce it. But if we're okay with just having a secondary or tertiary carbon attached to the benzene ring, so something like that, then we could just do that directly from the secondary 2-chlorobutane. So how do we reverse engineer a Friedel-Crafts alkylation? Well, if this is a tertiary or secondary, I don't want to say this. So if we want to figure out which one we did, we cut the bond and we look at what we have. And we see if we attached a chlorine there, would it be primary or secondary? So if we attach a chlorine to where we clip this and it's secondary or tertiary, we can do Friedel-Crafts alkylation. So we just put a chlorine on there and we would run the reaction with FeCl3. If we cut it and what we end up with is a primary chloro, we would attach that double bonded oxygen, do the acylation, and then follow the acylation with a subsequent reduction. So that's Friedel-Crafts in a nutshell. It's a way of creating a carbon-carbon bond between the benzene ring and some chain we want. The acylation is used when we want hydrogens on that carbon that's attached to the benzene, and we use the alkylation if we're okay with that carbon having like other carbons attached to it. And there's definitely other chemistries we can do. We're in organic too, we haven't gotten to aldehyde chemistry yet. So if you wanted to do that to be an alcohol, you could do the acylation and subsequently hydrogenate the double bond. But for now, we only consider like alkylation of the benzene ring. You're welcome. Now, the only way to make these problems harder is to put directing groups on there. So your alkylation is definitely an ortho paradirector, and if you've got something that's meta to it, probably that's going to have to go on first. right, so that's the end of the live stream. Again, if you ever have questions, feel free to ask. We got one live stream tomorrow afternoon at 2:30, and then that's pretty much it for live streams. Don't forget, your exam is due Sunday by midnight, and I will see some of you tomorrow.